Here he is. We're live. Let's see what happens. Oh, here's the unveiling of our 470 students. Gabe, do you want to turn off just the second from the top switch so we can see it a little better? Let's see. We need to do our animation transitions, right? Okay, for our guy running. And then what else did we say we were going to do? We looked at the state machines. We talked about okay, and we talked about triggers for animations. Okay, that's part of the animation thing. Okay, just do this later. Okay, so let's open our project. There's a slightly different version number on the Mac than there is on PC. We shouldn't have that problem moving forward. Okay, so see that fine? It looks okay. So let's go ahead and hit play and see where we left off. Oh, I think I remember we left a purposeful compiler error, right? To remind us where we're going to start. So let's open up our scripts here. Go to our baby movement. I had to reinstall Windows on it last night. I had the developer preview on there. I was messing around with mixed reality stuff, and then all of the screen capture things didn't seem to want to play nice with a buggy operating system. So I took that off. Okay, I think this should resize my text here. There we go. Real-time cool feature of signing into your Microsoft account on Visual Studio. I don't have to sit there and hunt around and find out. I increased the font the first time I did it. Now it's the bigger size. The funny thing is, I don't only do this for the presenting of it. I also require this to see it in the first place. Okay, so we've introduced an error somewhere in here, right? We were looking for our jump. Oh, right here. Yep. So this is for our jump guy, right? So we are trying to make jump work. So when we hit the space bar, we're going to do we're going to create a vector two, because similar to what we did here with our add force for our movement, we figured out what movement was on the horizontal. The movement of the horizontal was relative to where our get axis was. So this is just a floating point number. All right. So we took that floating point number and then decided where we were going on it. So in this case, we are moving 0 on the X. And now we want to give a force on the Y. So let's just come up with it first. See what that does. So we're going to say, let's just say 50. All right, so that's going to be our up force. I have a feeling it's going to be way too much. So if you just do 50.0 normally, C# detects that as, well, Visual Studio detects that as that you're trying to use the double. So you put a little F after that to flag it as a float. This kind of goes back to this idea of, when I was first teaching you, and those of you who are in 250 right now, we've recently talked about floats and doubles and those things, and how most modern languages, you're going to use an int unless it's not big enough. You're going to use a double unless um, it won't fit inside of a double if the value you're trying to store is too large. Then you can go to an object type that can hold it. But it is kind of interesting that doubles have become the standard for decimal point value storage, because the double is kind of the long of the floating point world. But in any case, because of that, when you do 50.0, it's saying this guy is a double, yet this function takes in a float, so you have to flag it with the F at the end of it saying this is a float. Okay, so that's going to create a vector2 up situation. There actually is a vector2 dot up that we might try here in a second as well. But in any case, we have a up direction. That's what this vector2 is representing. Okay, we haven't used that direction to apply it to anything at this point, but that's what it is. So now we're going to apply a force to our rigid body. So we have this dot RB, our rigid body, and we're going to add some force to this guy. And the force we're going to add is going to be a up force with no multiplier, with no multiplier. Okay, we're going to have to change this. This is some. So what we're doing is we are just adding a force of 50 float in the upwards direction, and know that our rigid body has gravity turned on, right? Therefore, that force that we're adding to that rigid body is pushing up against gravity when we hit the space bar. Now, just for debugging purposes, I'm going to go ahead. I'm going to do a print jump inside here, just in case it doesn't give us the behavior that we're interested in, that it doesn't look right, just to confirm that we are getting inside of this if statement. Make sense? All right, so go ahead and save that guy. Go back over here to Unity. Run this. All right, there's our baby. Way too much force. Okay. But he clearly jumped. So let's go back and let's tweak it just a little bit. Huh? Oh, yeah. That's true. That's true. Let's give him some mass, because we took that off when we were trying to debug his falling over stuff, right? Let's use auto mass. Okay, so now we need to adjust that speed again for movement. I wonder what auto mass sets him to. Oh, it showed up in there. Oh, there. All right, so we need to fight against a mass of 3. So let's look at our script then for our movement, because here's his speed right now. Let's just set the speed to 1 instead of the 0.001 thing. That. Let's set the speed to 10. Do we have to set up the drag? We freeze the rotation there. Angular drag. much higher value on, let's make it 1,000. So he can move it 1,000. Let's change it to 100. And all we're doing here is we are scaling it based on his, because his mass was off, that's why we had that weird speed of like 0.001, because it didn't take much force to push him, because he was light as a feather, so to speak. Well, now he weighs probably like a fat baby, and now we're having to add more of a realistic speed to it. I would say that still feels a little quick, so maybe like an 80. Okay, I think that feels all right. So now, let's mess with our jump force. Take our jump force. We currently have 50. So now with the new mass, well, that actually isn't even enough to get off the ground. Because remember, we have a force pushing down on us constantly. So just so we can tweak it without having to go back into the code, if I want to change, if I want this guy to be maybe something called jump power, how do I expose that to Unity so that I can tweak jump power on the Unity side of things without having to keep coming back to code and changing my 50 to 80 and that kind of stuff? What do I do? Good. All right, so we're going to go up here in Unity. We're going to give ourselves another public variable. This guy will be a float. We'll call this guy jump power. All right, so that exposes it, gives us like a little text field in Unity. So that down here, we can now use this dot jump power as our speed dealy, or our power dealy. Then in here now, for our script, we're going to get a new variable, jump power. We saw that 50 wasn't enough, so let's make it 100. My suspicion is let's make it 300. Just get him taken off. Oh, there is a hop. That's a fat baby. Okay, that is baby after my own heart. Okay, so let's see. So based on that, I'm guessing something like maybe an 800. Give him some lift. That isn't even that great of it. Oh, now what's interesting there is it's not detecting every single time. And part of that is because of where I have the, so let's see, when we hit the jump. So it did not detect it that time. Didn't get it that time. Any of these times. We have this inside of fixed update. So it's only going to be when we have the key pressed down. So I suspect that if we held the key down, he would jump. Okay, so we're getting pretty inconsistent behavior on jumping. So right off the bat, what could we do to hopefully make jumping a little bit more consistent? what seems to be happening here with the spacebar. This really isn't a jumping problem necessarily, right? It's a detecting the spacebar was clicked problem. So right off the bat, what can we do to what are some strategies we might use to alleviate some of this issue? Go ahead. Ah, yeah. So fixed update happens some period of time. So there's delays in between. I think Tim had told us that it tries to mimic 60 frames a second, so that it kind of tries to become a even playing field for everybody. Um, where update happens once per frame. All right, so you're suggesting maybe we move the jump into update instead of fixed update. All right, let's go try that. So that's the comment for update, even though we have it on fixed update. So we're going to have our update method here, and I think it's okay to have it private. Here. All right, so now this code will happen at 60 frames a second. This code up here should happen every single frame. Rocket landing, baby. Okay, so that seems to give us a better behavior. So let me ask you this question: why wouldn't we, or what would the downside be to move our movement here into update instead of fixed update? I don't think it would break anything to have an update. It would just be more of a performance issue, right? You're going to have to process this stuff every single frame, which might not be that big of a deal because you're still, when you get the access value between two frames, there isn't going to be the jump between every 60 frames. It's actually not 60 frames, but it's 1 divided by 60 frames. So 1/60th of a second is how we would. So the difference between 1/60th of a second and let's say this is 120 hertz monitor. So the maximum, I'm guessing we're probably running this game at 120 frames a second. This is pushing the graphics card on this guy. Um, but so the difference between 1/120th, 1/120th versus 1/160th twice as often, right? Well, is there a drastic? So how far, when we think about our keys here, how far are we changing that x-axis in 1/60th of a second? Not very much, right? That's what we're currently doing. Well, how far are we changing it in 1/120th of a second? Less, even less, but it still changes a little bit. So is it worthwhile processing this stuff twice as fast? We are probably not going to notice it from a human being's perspective. Now we got to think about the performance difference here. Having said that, when you deal with player movement, that's a pretty important part of our game, right? Don't we want that to be as fast as possible? One side of the argument. We want it to react. If the player says move, you want it to move immediately. On the other hand, though, especially when you start talking about some of these esports games, right? You want everybody to be on an equal playing field. But does reaction time change equal playing field? So you might have two players, and one player might have significantly faster twitch muscles, or they can react significantly quicker. Their hand-eye coordination is faster. They press the buttons faster, whatever it is. That person would and should have an advantage in a game, right? Otherwise, I would assume that me and Usain Bolt would be pretty similar in speed if he didn't get off the line so quick. It's really the issue. Yeah, I mean, if I beat him off the line by 15 or 20 seconds, and I got real close to that finish line by the time he started, I'd have a chance. I recently saw some video, some documentary that was talking about the speed of cheetahs. They had a cheetah race. They had two different things. They had just flat out speed, and then they had also like banking. They brought in some NFL players that were not as fast as Usain Bolt in a dead run, but they're agile, right? They can go around stuff. So they had the cheetah do do these obstacle courses. The cheetah definitely beat Usain Bolt. And then they showed how far he would have had to have. And I think Usain Bolt would have had to have. I think what's his 50 meter? Like that's or is it the 100? What's the one that's like supposed to be the fastest? 50 or the 100, something like that. 100. Yeah, the super sprint, the sprint one. I think he would have had have almost like a halfway head start before the cheetah would beat him. And then the cheetah beat the NFL guys most of the time. I think the NFL guys won one of the times. So that was closer. But the cheetah, I guess, says that they use their tail a lot for banking. That's why I don't bank as much. My tail is too short, so it's hard for twists and turns. All right. So with that in mind, would this be okay to put our movement back and forth inside of update? Let's go ahead and do that. See if we notice a difference. Now, one thing we see is our baby's moving faster. We're applying a force twice as often, right? Because it is a cumulative force. Now, that's okay. It's not the end of the world, right? So what do? We just cut our force in half. Instead of a speed of 80, we have a speed of 40. Now we should be right back to where we were. Mario do that? Mario Brothers, if you're like coming up to a thing and you turn around, you immediately turn around, or sliding to a stop? I don't remember. Yeah, okay. So that's the answer I was hoping for. So how do we fix this? If he's going to the right and then I change directions back to the left, and I want it to be a turn on the dime type thing. I mean, right now when I'm so it's somewhat the ice skating, right? When he goes to the right and I let go, he just keeps going because he has an accumulated. Because he has an accumulated force that has built up. So when I let go of that button, I need to have that force be zero, right? So how do we get the force to be zero? Let's look. I think I can print this dot RB dot I think we're going to have to keep track of the force we've built. we come up here and we make a private variable called horizontal force. We start this guy off at this guy's going to be a float. We start that off at 0.0 f. Here, and before we add our movement, we're adding a force. We're going to say this dot horizontal force plus equals movement times speed. Force takes in a vector 2. So we actually want this starting point, this horizontal force, to be a vector 2. Dot. Well, let's look at it anyways. Is there an identity? So that's a 0 force vector 2. We just want to see how that changes. We're going to print it out. So now before we add our force here, we're going to say horizontal force plus equals movement times speed. So this guy right here, movement is a vector 2. So that's a direction. Speed is a multiplier on that direction. So it's ultimately this is going to be a position. That's what vector 2s are, right? So when we add a force to get us to a position, we're pushing us in that direction. So we want to see how horizontal force builds up. I'm going to go ahead and I'm going to print this dot horizontal force. I wonder if it knows how to print that. Print out the X and Y directly. All right, so let's just see how horizontal force builds up. Look at what that guy looks like. Okay, because it is a cumulative thing, which is why we need to try to slow down when we turn back the other direction. All right, so right now, you see the force is 0, 0. I'm going to push it a little bit. Okay, now the force is 347, 0. So that means he's not going up, but he's going over some. Okay, but now he's holding there because I've let go of the button. Right, that's the new position he's on the x-axis. Now, as I do that, I bring him back. So notice it going back and forth, back and forth. Now, if I let go, I'm no longer applying force. He's slowing down based on the drag of that surface, right? So the surface isn't sticky. Now, one thing we can do is we can say, okay, well, let's add the drag up so that if we're no longer applying a force to him, he'll skid to a stop, but then it'll also be harder for us to get started. We're having to push against that drag. So what we really want to do is we want to have the ability that when we let go of that button, he stops. So rather than turn on a dime right now, we want him to actually completely come to a stop. Now, if we look at that force that is currently on the thing, while he's still moving, The force was building up. And now the force stops, but it's not at 0, 0. He's at a fixed position. Okay, so add force is somebody shoving you from behind. Okay, you're like on a sled and we're pushing you. So how can we get this when I let go of this button? I want this baby to completely stop. How would we pull that off? If I'm running forward at 10 miles an hour, okay, at a obviously massive 0, I'm running forward at 10 miles an hour, and I want somebody to stop. I want to stop. What has to happen? Okay, I got to run into a wall. Okay, counterforce. How much of a counterforce? Yeah. So if I'm pushing this way and somebody else is pushing back at the equal force, I'm not going anywhere, right? Okay. So I can apply a force in the opposite direction that's equal to the force I'm currently moving at. Now, at what points? Now we gotta see how does the accumulation of force work, because we see the baby here. When he stops, we see that force is stuck, right? So he's at 3066.9 on the x. Okay, so that's the accumulation of force that's been pushed onto him at that point. All right. So now, if I want to stop immediately, is it going to be good enough to just put a force in the opposite direction instantly? So let's look at that. So rather than us getting the axis, we get the thing that we let go of the right arrow. Let go of that button. We immediately then apply a force that's opposite to the force we currently have. Will that stop us? So should we stop? Is the question here. So we can ask the question if input dot get key down. Actually, it's going to be get key up, right? We let go of that key. Which key? It's going to be key code dot, probably call it arrow right or something. Right arrow. Right? So if the right arrow key was pressed, we want to do something. So we want to apply a force maybe in the opposite direction of our current force. So can we say this dot RB dot add force? And what force are we going to add? We're going to add this dot horizontal force times -1. The inverse of our current force. Seems like a reasonable thing for us to try, right? Okay. Remember, we're dealing with a physics engine effectively here. So we need to play by the rules of physics, or at least the simulated rules of physics that the engine creates. So make sure you save this. So now when we let go of the right arrow, and actually let's do a print in here. We're going to do print, hit the brakes. We let go of the right arrow. We're going to immediately apply a force equal to our accumulated force up to that point in time and see if we can get him to stop. Left button we haven't programmed yet. So let's go back and try that one more time. Oh. What else do we need to do? When we stop them, we need to zero out our accumulated force. Make sense? Otherwise, the baby kind of stops. We got the Superman shove. get that coming. We might be able to use that effect for some sort of like weapon, because obviously the baby's going to be fighting against some like really high tech robots or something like that. That's what zombie babies do. Okay, so hitting the brakes seems to be mostly working, but after we apply our horizontal force, we need to now zero out or our horizontal force. So it's no longer an accumulated value. Baby has stopped. There is a little bounce back there. What's that from? I think that bounce back is from. Well, so this is happening every single frame, right? So when we build up a horizontal force, in that time when we're letting go of the button and it's processing that, as that button is being let go, and let's assume that maybe the very first part of letting go of that button is what fires. At some point in there is when that event of button up actually fires. What's happened with our what's potentially happened? We potentially had some additional movement on the X that's done some buildup. So we have this little extra horizontal force that's been built up. So this is giving us pretty close to what we want, but not quite what we want. And I don't remember, does Mario kind of skid to a stop at least a little bit? He stops, right? Or at least he might. We might want to create that effect of him actually stopping. So what are we doing here? We're playing this game of timing. That becomes dangerous in game design. If you're playing, I think I used the example the first days of the class about the game Double Dragon that I played when I was a kid. We got a new computer, and game designers of that implemented things in terms of timing. Really, they implemented it in terms of frame rate. Well, at least I'm presuming it was frame rate, but that became a very problematic thing. Happened a lot faster on a faster computer. And same thing's going to be true here. We're going to have less of the skid effect. I mean, this monitor is a 120 hertz monitor, which is a good gaming monitor, but it's not the fastest. It's a 240 hertz monitor, right? So that 240 hertz monitor is probably going to have more of a skid effect. We have more frames per second. Well, assuming you have a good enough graphics card to push 240 frames, right? So we're assuming frames are happening more often. So if we have 240 frames per second, now there's more time between when that I'm letting go of that button and when the actual update is occurring, right? For me to have built up some additional force. Now, what if I move that side-to-side movement back into fixed update? That should give me a consistent thing. At the same time, if I build up my horizontal force, so if I take, now I'm going to leave the should stop code inside of update. I want to be able to hit the brakes immediately. Quickest we could possibly do something is inside of update. All right. But what we're going to do is we're going to move this movement stuff back into fixed update. All right, so in fixed update, we are doing this, how far should we move horizontally, blah, blah, blah. And we are accumulating our horizontal force. I'll go ahead and stop printing that because that actually is also hurting our performance. That's creating even further delays before we're taking actions, which is giving us more time for other things to occur. So we're going to take out those print statements. Take out the jump, even though we're not jumping right now. So in update, checking this once per frame. Should we stop? If we should, we're going to apply whatever force we currently have built up times -1, so the exact opposite force, i.e. the wall. And then the horizontal force will reset to 0. The hope is, since fixed update should be happening no more often than that, right? At the very least, these guys should be happening either as often as each other, or update happens more often than fixed update. See what behavior we get from that. Maybe see a more consistent. All right, so one thing we're doing here is we are playing with force as opposed to playing with position or acceleration or velocity. So force is relying on physics, right? So this is something being pushed against you. And we're mostly getting that effect, right? But really what we're seeing here is almost like the wall effect. If you run into a wall hard enough and you have a mass, there is a bounce effect to that. You've heard like those skydiving stories. There's some comedian from years ago that tells some. Hopefully, it's not a true story. It seems like it might be impossible. So it's probably not a true story. But some skydiver, skydive, chute didn't open, hit the ground, bounced twice, and lived. Something like that was and he's like, do you know how hard you have to hit the ground to bounce one time? To bounce twice seems to be unlikely, right? But I mean, if you bump into a wall, even at a moderate speed, there's going to be a little kickback, right? Because all your force that you had going into that, I mean, you're kind of a spring, right? You get muscles and bones, and those things press a little bit, they're going to push you off. So as long as that didn't happen too hard, where things are damaged on the inside, there is a bounce back effect because that instant force is being pushed back on us, and we have momentum. So I think what we're kind of seeing here is that momentum. We're stopping ourselves, right? We didn't get through that wall. We hit the wall, but we bounced off it a little bit. Now, if we want to stop right at the wall, because that's really the difference here. The difference here is our zombie baby isn't actually hitting a wall. We're portraying that behavior, right? We're putting an invisible wall in front of the zombie baby that is going to push back at the exact, unless the baby can overtake the power of the wall, which we're giving it. We have an infinite wall at this point. We're giving it the exact opposite force that we've accumulated. But so that can't happen in our model here. But we are putting up an invisible wall to stop the baby. Now, in real life, if we're the zombie baby running along the ground, the way we stop isn't to put up an invisible wall. We hit the brakes. We change our velocity. Now, in real life, what would we do? We would decelerate at a speed, right? So we would have kind of a force that pushed back on us that we would kind of decelerate at that speed. So it might take 2 or 3 steps for us to stop. So now you're telling me, though, in the original Mario game, whether this is true or not, Mario could stop on a dime. I kind of do remember in some of the later Mario games that when Mario went to stop, there was a skin, there was actually an animation associated with it. Like, I think Mario Brothers 2 maybe, which coincidentally was my favorite Mario Brothers. A lot of people hated Super Mario Brothers 2 because it was so different than the other ones. But I thought that was the most interesting. But in any case, when he turned back, he kind of had a skid effect. But I don't know if that was actually a movement-based skid effect, if it was just an animation thing, where like Mario was hitting the brakes, just like a hockey stop, something like that. But if we're thinking about real life, we kind of slow down, right? We're applying a force to ourselves by kind of stopping ourselves with our muscles. But it's not an instantaneous stop. So now we're trying to kind of defy real life here, but that's okay. We get, as a programmer, we get the advantage of being able to do something like that. So we want to be able to change the current velocity of our dude, right? Speed he's currently moving at right now. Now, when we apply a force, that translates into velocity, right? When somebody shoves you, you start moving in the opposite direction, and how fast you're moving is your velocity. It has something to do with how hard you were shoved, but they're not directly related. One's a cause and effect. Does that make sense? So we want to look at how can we change the velocity of a rigid body. So look at the documentation. So we're going to say unity, rigid body velocity. So we have a value for velocity, and the velocity, the default velocity, the one they're showing here is vector 3, because almost all the examples you're going to see are going to be 3D example stuff. I think we mentioned before that Unity was originally a 3D engine, hence Unity3D.com, but they've added a whole bunch of 2D stuff, mostly for mobile, because I think 2D games have become very popular in mobile, and they're kind of making a comeback because of that. So what we're going to do is we're just going to set the velocity. We don't care about the forces that have accumulated up to this point. We're going to set the velocity to 0. So let's go back. So inside, and actually because we moved back to fixed update, the speed of our baby is going to be half of what it was before, right? So we'll have to double the speed again if we're going to leave it inside of fixed update. If we want to move it back into where we had it, we'll go ahead and do that now. There isn't a great answer to that. By moving it back, we're saying this our guy can change, can move as fast as the player controlling him, the human controlling him, can tell him to. Because at that point we're limited by frame rate of the computer, not by if Tim, who I assume probably has faster video game reflexes than I do, he was just laughing. Say, look, you don't think I have good video game? Say, look, I'm already pressing the button without even thinking about it. Look at that. Yeah, see that? It's not even fake. I am pressing that button without even thinking about it. I've built-in reflexes, God-given reflexes. Doesn't even take effort. So, but the point is, let's go off this original thing, that his reflexes in video games might be faster than mine. Okay? So with that in mind, there's a chance he might be able to do something within 60 frames a second, or maybe I can't. Right? So with fixed update, there's a chance that he might be limited by that 60 frames a second, where the movement he tries to make doesn't happen as quickly as he's capable of making it happen, because he's only checking 1/60th of a second. Now we're saying, look, it's happening every single frame. If you're beating the frame rate of your computer, you probably have a crappy computer, is what it is. I mean, I don't officially know if there's some pretty crazy gamers out there. I suppose there might be some guys that could beat the frame rate of the computer. It seems unlikely. It might be possible. I don't know that it's not possible. It just doesn't sound right. Okay, so we'll move it back to update. This will make it as quick as possible. We will have to make our speed associate with that because now we're applying our speed as a force twice as often. Here. Okay. So now, this is our movement. The should we stop rather than applying a force, which is putting up the fake wall. We're instead going to say this dot RB dot velocity. We can also get the velocity of our guy. Okay, but we're going to set the velocity here equal to a new, and actually let me just check real quick. I'm pretty sure the velocity for a rigid body 2D is going to be a vector 3 or a vector 2. Yeah, it's a vector 2. So when I hovered over it over here to the right, it shows me what that function would return. Because it's a rigid body 2D, it'll give me a vector 2. If it's a rigid body, a normal rigid body, which is a rigid body 3D, it would give me a vector 3. So I'll set the velocity of this guy equal to a new vector 2, 0, 0. He's not going anywhere. Make sense? That's if we let go of the right arrow. Save that. Go back out here. Start the baby running. Stop. Now, we have an opposite effect. Baby did stop. What happened? Now, one thing we might have, I mean, first of all, if I just tap the button, to hold it for a second, does that kind of look like what happens when the baby is running there? It kind of looks like what's going down, right? So go back into our code here. We're asking the question if we should stop. Because that's what we want to do on that frame. If we're not stopping, I'm going to throw an else in here. Because we're still reliant on timing here. And what have we done? We've actually built up some additional force. So if at the beginning of this frame, we still had the button down, we've added a little force. Then we let go of the button. Same frame, right? We've let go of the button and we set the velocity to 0. But now that force is being applied, and that happens over a series of frames. We still have a little shove, a little momentum moving forward. So what we really want to do is we want to say, if you want me to stop, stop. Otherwise, let's see if we should be moving. Don't let them both happen in the same update, unless they should. Make sense? So I'm going to throw in this else, our movement stuff, and see if we can avoid any extra force being added to that baby as we are stopping his velocity, effectively making his velocity more than it used to be. But we've already seen that velocity is a decreasing element with add force, right? It automatically decreases. That's part of the physics. When somebody shoves you, you go back initially quickly and then you kind of slow down. Part of that is because you're hitting the brakes, you're trying to stop yourself, but also other, when you finally fall down to the ground, that's going to stop you. You might bounce a little bit. That's a pretty hard shove, but the point is it's trying to mimic how physics actually works. So now in this particular frame, we're going to say, if If I'm supposed to stop. Otherwise, are we adding any forces? Unity. Sliding. What's the deal? The deal is. That's the speed, that frame, which the baby's actually moving. We've already said that the force is an accumulating effect. When we add a force to something, we add a force. So we're going to shove at speed 5. That's going to get the baby moving. And then over the next several frames, that's going to be sliding to a stop, right? So that's calculated at the time the force is added. So they're going to figure out, okay, well, what's the baby going to be doing over the next 10 frames? Let's just use 10 frames as an example. Okay, we add a force. Here's the baby's velocity over the next 10 frames. Well, we set the velocity to 0 in frame 8. Frame 9, the baby's velocity is going to be whatever add force set it should have been. So what if we put these two things together? We immediately give it the opposite force and then set its velocity to 0. All right, so we're going to say this dot RB dot add force. The force we're going to add is this dot horizontal force times -1. Then we're going to say this dot horizontal force is equal to new vector 2, 0, 0. Reset that horizontal, that accumulated force, and then stop the baby's velocity. We're back to the slingshot effect. At least he's not sliding forward anymore. Now, this did give us the effect that we wanted. Just we overcompensated, right? He's not sliding forward anymore. Maybe we shoved the baby a little too hard. Now, the velocity of the baby is a vector 2D. What if we applied a force that was the current velocity of the baby times -1? An exact opposite force relative to the baby's current velocity. Back in here. So we don't need to even mess with horizontal force. And let's also not set the velocity to 0. Setting the velocity to 0, that velocity it becomes a constant, right? So we're saying your velocity is 0, but now we're still feeling the effects of a previous add force. So we need to counteract that previous add force with a new add force in the opposite direction. But rather than give it the accumulated force that we've pushed the person, right? That we pushed the baby. We don't want to give it the whole force back. We've seen that pushback, right? Instead, we want to give it the necessary force to stop it, which is going to be based on the current velocity of the baby. So we're going to say this dot RB dot velocity, which is a vector 2D, times -1. However fast the baby's moving right now, I'm going to shove you back at that exact velocity in the opposite direction. Try that. Ooh. I don't even know if that's slowed him down at all. Let's print out velocity there. More than that. I don't. Well, I don't think we need to set it to 0 because the whatever the velocity is, when we push back at that exact same force, the I would have thought it would have canceled it out. That was my expectation. Let's print this dot RB. Maybe I have a misunderstanding of how rigid body 2D is working. Let's find out. So now when we let go of that arrow key, we're going to go ahead and print out what the baby's current velocity is. Let's see what that looks like. Based on the behavior we got, the velocity appeared to be 0. That's what it looked like to me, or a really small number where that force did nothing. All right, so it was 7.2. 7.6. Let's get the baby going pretty. 12.6. Okay, that's a legit value, that velocity. If we push back at that same rate, let's try what you suggested. Maybe because that pushback happens, calculated over several frames, doing the pushback will inverse that calculation, but then setting it to 0, I suspect we're going to have that same problem. So we'll go ahead and add a force to the rigid body opposite its velocity, and then set its velocity right now to 0. Hopefully those, if it's sliding forward this way, we push back this way at the equal force, that counteracts the forces for future frames. And then we set the velocity, the current velocity to 0, which will stop them from moving. That's the hope that that's what that does. Still a slide forward. I can hit the brakes if I turn back the other direction. Remember before we had a thing where when I went to turn back in the other direction, there was a lag time. The baby slid kind of, then came back as we were catching back up. But I mean, I could stop on a dime. What I really want. We've lost the baby. Really want to be able to let go there and have the baby stop moving. What if we set the velocity? Now we're trying to short circuit the add force. What if we set the velocity to be the current velocity times -1? Let's not add the force for the moment, and I'll take out this print statement. Right now, we're not going to try to add the opposite force. We're not shoving the baby in the opposite direction. Instead, we're going to set its velocity to be the inverse of its current velocity. Now, because we've seen him basically come to a stop at 0 and then slide a little bit, I expect this is going to give us that weird, what appears to be a bounce back effect, but he's just going to move in the opposite direction. I just want to see that that's the behavior we get from this. Mm-hmm. Oh, because this wouldn't have been an accumulative. But this else should not happen in the same. So you're thinking it is picking this up in the next frame. Well, this guy gave us a speed of. This did slow it down. Unless we did. What if we did this? What if we set. Going off of what you're saying, we set the velocity to 0. Then up here, we add a force, not the current velocity, but instead current horse, the inverse of this. Times speed. So I'll grab the horizontal movement that we currently have set, and then I'm going to add force of that movement times speed times -1. Push back at that exact rate. Then immediately set the velocity to nothing. But you're saying that if I remove the, if I take the plus off of, not that, if I take the, I get it. I get it. Because what we're doing is rather than push back with the accumulated force, we're pushing back. So you're still calculating movement up here, right? You were doing it down here. So rather than giving us the, so this actually then becomes a constant. Well, no, it won't be a constant because movement will change. It'll be whatever it was. Oh, that actually makes it, that makes perfect sense because it's that horizontal force is whatever the force was the previous frame, which is exactly what's necessary to push back this frame. That makes sense. So before we were accumulating our horizontal force. So now instead of accumulating our horizontal force, what we're grabbing here is what was the force the last frame? Okay, what horizontal force did we add to our rigid body the previous frame? And whatever that guy was, we can add the inverse of that here times negative. So times -1 will give us the inverse. So there's the horizontal force. So that's times the -1. Now, my feeling then is you probably don't need to set the velocity to 0, but there might be a skid effect if you don't. because the rigid body is a cumulative effect. So this will undo that cumulative effect, negate the cumulative effect, but then this stops us now, visually. Battery is running low. How far we made it almost the whole class. Okay, so let's see this. And what's your mass? Yours is 3. So you're grabbing the horizontal force, the previous one. You're adding a force to the rigid body that is the previous horizontal force. Now, do you have this in the if else? Actually, there could be some truth in what you just said. Because, and not that it's crap for MacBook, but because this system is set up as a gaming keyboard, I think that they are analog keys. So there's a such thing as a half key press or something like that, where maybe your typical laptop is going to be very discrete keys. So there isn't that divide. That's actually, I don't know that that's the case, but it's at least plausible. I'm going to try to set the velocity to 0 first, and then apply the alternate. Oh, no, that should break it more. That's what that's actually going to do. That's going to break it more. Oh, it actually didn't break it more, which is interesting. That would have set his velocity to be a stop, then push back. But because these guys don't necessarily, they happen in the same frame, so these guys aren't necessarily guaranteed to happen in this order or something like that. Okay. So this will be interesting. So about half of us have MacBooks and half of us have Windows machines. Go ahead and bring your game, whatever your character is, up to date with this for your movement. And let's see if we get a different behavior between Unity on the Mac and Unity on the PC. So if you have some skid for a stop, that's okay. That's acceptable. We have this working up to a point where, typically when you want Mario to stop, the reality is you're not just going to let go of the key. You're usually stopping and turning back because you're about to hit the wall, right? You're about to fall off or something like that. So we mostly have the effect that we need. Now it's a matter. Now I'm interested in what the effect is. So whatever your current game is, we want to make sure we have movement in your game. Whatever characters you've used. And I encourage you not to necessarily use the baby. Create a game in your own image, if you will. Go ahead and get your forward and also your reverse movement. So go ahead and add the code for that, letting go of the left key as well. Go ahead and put that up on Blackboard. All right. I will see everybody on Thursday. Just on the bright side is Unity definitely moved faster on this by a lot. Huh? Okay. Does he? Okay. So it's not on a dime. So it's possible. Well, we can do that though with going back the other direction.